We were discussing about this, different atomization techniques in the last class, and we have discussed in the last class about capillary drop process, which deals with the mechanical disintegration of the liquid film in the form of droplet and subsequent powder production. And then we have also discussed about the electrodynamic potential based disintegration of melt film in the form of droplets. So, we will start with the atomization assisted by liquid, that means by with the jet of water or with the gas jet. What happens in case of atomization by liquid? So, if you see the schematic, so you can understand this is a typical example of water atomization. So, you can see over here that this is the tun dish from which the liquid column liquid melt is coming out. So, this is the diameter of the melt stream which is coming out of the this tun dish, and then these are the two jets which are basically kept and which are impinging the high velocity water jet, and which is facilitating simultaneous cooling and as well as disintegration of this liquid film, or the, and then we are basically seeing the fine droplet formation, and then these are getting deposited towards the at the end in the form of powder particles. So, it is the flight path. So, this is the flight path of this powder melt droplets. So, during this path these melt droplets are losing their superheat and they are undergoing solidification in the form of fine powder particles and then deposited at the base of the tank. So, liquid, generally water is used and gas also is used. So, these are two atomization techniques are crucial for industrial powder production, because they are largely responsible for all the powders which generally being used by downstream powder metallurgy based techniques. And also of course, for additive manufacturing, of course, there is a variant called plasma atomization. So, we will talk about that as well. However, it is still limited to very few countries in the world, and its production of powders by plasma atomization is still not that popular because of the capital investment involved in that case, whereas plasma and water and gas atomization based powder manufacturing techniques are quite popular, and so it is being practiced in a widespread manner. So, the process description, so the metal is melted in a separate furnace and flows through a tun dish like you can see in this schematic, and then it is basically getting disintegrated by the impinging water jet in case of water atomization. So, the water jet configuration, so the number of jets and the included angle, that is alpha, between the jets and the melt stream, and the local arrangement of the jets significantly affects the atomization process. So, the operational parameters, so water jets can operate at pressures in the range of 6 to 21 MPa, achieving velocities in the range of 70 to 250 meter per second. Metal throughput ranges from 10 to 100 kg per minute with 0.1 to 0.4 meter cube per minute water consumption. So, these are some of the operational parameters which are necessary for success of water atomization route and subsequent powder production. So, efficiency, so despite better efficiency than mechanical disintegration, the overall process efficiency of water atomization is still very low, which is as low as around 1%, which is alarming. So, gas atomization is the second most important atomization process. Air, nitrogen, argon or helium can be used. So, other than the use as a disintegrating fluidized media as these gases, the other architecture of the entire device is pretty same. So, in this nozzle, in case of gas atomization, in spite of water, we use this highly pressurized air or nitrogen or inert gases such as argon, helium, etc. So, depending on the requirements, determined by the metal to be atomized. So, the key requirement is that the metal should not, the melt which is we are basically using or considering for disintegration, the powder preparation should not be having a chemical reaction with the gas that is being used for as a disintegrating fluid media. So, satisfying the criteria, we can use the appropriate gases, and atomization is undertaken either in vertical or horizontal units. the process principles are similar to those of water atomization as told before, and an empirically derived relationship between the process variables and the mean particle size of the droplet aka the powder particle that we can determine from here. So, it is the droplet diameter dd is equal to c ds, that means diameter of the liquid column, and into root over vs gamma s by vg. So, this is the velocity of the melt stream, this is the velocity of the impinging gas stream, and here there is a mistake, please correct it. This is the viscosity of the solidifying liquid melt stream, and this is the diameter again, and then 1 plus qs by qg. So, this is the discharge terms of the for the gas and the liquid melt, solidifying liquid melt. So, so here this v represents the kinematic viscosity, g is the index for the atomization gas, again a high velocity of the atomizing fluid, small melt stream diameters, high density and low viscosity and surface tension of the melt favor the production of finer particles, where the factor c is dependent on, so it is basically a constant. And so then so once we have discussed about this fluidized media based disintegration of the melt droplets, now we move into the centrifugal atomization. So, centrifugal atomization, so this process also like capillary drop formation process, it can be a single step process, it can be a two step process. So, so what are the so in this case basically it uses a centrifugal force for melt disintegration and operates in either a single step or two steps. So, in case of single step, a rotating consumable alloy bar produces a liquid film disintegrated by an arc plasma or electron beam. So, in case of single step process, it is you can, so it is basically the electrode which is undergoing a centrifugal motion, and that is basically responsible for melt formation and also rotating with the centrifugal and exerting centrifugal force to the fluidized melt, liquid melt, and facilitates their disintegration in the form of droplets. So, so that is why it is called a single step process, and so sometimes it is also challenging because we are talking about a consumable electrode, consumable bar which is basically responsible for this centrifugal atomization. So, it requires the bar rotates at very high speeds up to 15,000 rpm and requires high stability and surface quality. However, this method limits the superheating of the melt that to prevent rapid runoff. So, so that is why you can understand that there is a limitation in terms of the size of the powder particles also that we can achieve, because we can hardly go beyond the liquidus temperature of course, but not much higher beyond, because in that case there will be spillage or runoff of the liquid from the consumable electrode in spite of undergoing the disintegration process, which is the intended need for achieving the powder particles with the desired shape and size attributes. So, in spite of that, when we talk about two step processing, so in that case it separates out the melting and the disintegration processes. So, melting happens first and then the melt is then disintegrated by a rapidly rotating cool disc, like it is the case which is shown over here. So, this is a typical two step centrifugal atomization technique. So, while this overcomes single step process limitations, transferring high rotational velocities to the melt is a challenge. However, you can see it's a typical micro mechanism of the disintegration is shown in the form in this pop-up box, where you can see the liquid, like initially we have discussed that liquid film, so you can see the disintegration of these liquid ligaments in the form of droplets at the onset of centrifugal force that is exerted by this rotating spindle or the wheel or the cup. So, disintegration mechanisms in case of atomization are like direct drop formation. So, at low melting rates, droplets are emitted directly, linked briefly by a fine thread that forms smaller secondary particles, resulting in a bimodal size distribution. That is mechanism number 1. Number 2 is ligament disintegration. So, that is LD. So, at higher melting rates, protuberances stretch into ligaments and that break into particle strings, increasing the proportion of secondary particles. So, and then number 3 is film disintegration. When the at very high melting rates, a film forms on the disc edge emitting droplets directly. So, these are the 3 different mechanisms that we observe in case of atomization by centrifugal action. So, the particle distribution, the mechanism of disintegration determines the particle size and distribution, with bimodal distribution in DDF and higher secondary particle proportions in LD, that is ligament disintegration, and film disintegration FD. So, a mathematical treatment of centrifugal disintegration can be done based on this equation. So, this is DD, that is the droplet diameter, is equal to 1 by 2 pi n root over 6 gamma s, that is the surface tension term, this is the density term, and this is the radius of the centrifugal disc. So, the main advantage of single step centrifugal atomization is that the melt has no contact with ceramic crucibles or liners. So, because it is, we are talking about the consumable electrode itself, which is responsible for melt preparation and also simultaneous exerting centrifugal force over the liquid film for its disintegration. Whereas, in case of two step processes, we are talking about melt preparation within using a ceramic crucible and then dropping of the melt into the rotating disc or wheel for two step disintegration of the liquid film in the form of droplets. So, the process is therefore suitable for the production of refractory powders like tungsten or highly reactive powders, that is titanium alloys. So, the production capacity is low, that is 1 to 6 kg per minute. And then so after we discuss the centrifugal atomization, we will move now into the vacuum atomization technique. So, the vacuum atomization or melt explosion technique utilizes the pressure dependence of gas solubility in metal melt. So, after vacuum induction melting, the melt is saturated at an enhanced pressure around between 1 to 3 MPa with a gas, usually hydrogen, and then a ceramic nozzle system is immersed into the melt to connect it to the elevated evacuated atomization chamber. The gas is spontaneously released and breaks the melt stream down into droplets. So, the resulting powder morphology is similar to inert gas atomized powders in both particle shape and distribution. So, then vacuum atomization is useful for particular melts where there is a risk of getting oxidization, and also when the impingement of the liquid stream or even the cool this inert gases may cause inferior properties and size attributes, or maybe chances of oxidation of the powder particles of the resulting that are getting generated from the melt stream. So, in those cases vacuum atomization fits the bill. And next is the ultrasonic atomization. So, so, in this case the main process variants for ultrasonic atomization are melt disintegration by ultrasonic capillary waves or standing ultrasonic waves in a gas. So, the former process utilizes stationary capillary waves at the surface of a liquid metal film for its disintegration into droplets. As with centrifugal atomization, so single or two step processing is possible in case of ultrasonic atomization as well. So, in single step processing, the liquid film is produced by plasma heating a sample placed on the top of the resonating electrode. However, in two step processing, the liquid melt is prepared like we have discussed for other cases also. So, it like in a tan dish from where the liquid melt is coming out, and then it is basically a ultrasonic source, and then there is a receiver. So, there are some pressure points like this where when the melt stream is passing through this pressure point. So, for example, it is the melt stream which is coming here, the melt stream which is coming here. So, so there are so the melt stream should be positioned in such a way so that it passes through these pressure points where this of the ultrasonic vibrations are maximum, and that can cause disintegration of the liquid film in the form of small droplets which can then get deposited in the tank. in a tank which is kept for collection of the resultant powder particles. So this way we can achieve very fine powder particles, although it is a costly process and it demands for specialized equipment. So in two-step processing, this is how we can achieve. So the standing ultrasonic waves can be generated and in a gas volume between an ultrasonic source and a reflector. So this is basically, if you can term it as a ultrasonic source, and then this one is, you can say, as a reflector, and then they are basically responsible for creating this ultrasonic wave, merging at these points and creating these pressure points, which are serving as a pressure point. So a metal stream poured through the pressure points of this wave field is disintegrated into droplets by ultrasonic pressure. So the particle shape produced by the above methods is spherical, and so it is finer and it is spherical, but still it is not as cost effective and technically feasible or viable in industrial applicability point of view, like in case of gas or water atomization. So hence these are still remaining as the most popular techniques. So we have we haven't discussed about plasma atomization here. So for your knowledge, I can tell you that plasma atomization is one of the most advanced atomization technique, where we are basically using plasma as the source for energy source for creating the melt pool formation, and then basically the disintegration also. After melt preparation, it is the plasma which is responsible for disintegration. There is also, we also use pressurized gases for disintegration, and then subsequent formation of, but we can achieve spheroidal powder particles in case of plasma atomization, which are having higher sphericity than any other powder atomization technique. So otherwise the process is very similar to the gas atomization that we have discussed before. The difference is the power source, energy source is plasma, which is responsible for melt preparation. Okay. So with this, now we will discuss about the solidification and cooling aspects of the droplets. So the cooling rate and powder particle properties. So cooling rates directly influence powder particle shape, microstructure and the size of the atomization chamber. So higher cooling rates promote rapid solidification and resulting in amorphous or refined microstructures in the generated powder particles, and the mechanisms of heat transfer. So cooling occurs via radiation and contact heat flow. So smaller melt volumes and higher heat flow favor faster cooling, whereas atomization under vacuum or reduced pressure yields slower cooling rates. Okay. So the microstructure formation, so the nucleation and growth rates control the particle microstructure. So high growth to diffusion ratios due to large undercooling, so it is talking about high G by R ratios, lead to uniform crystal structures, while low ratios results in dendritic structures with segregation. And here, like, dendrite arm spacing is also connected with that, as we know that when we have higher cooling rate, we get achieve lesser secondary dendrite arm spacing, and simultaneously with the lesser cooling rate, we achieve higher secondary dendrite arm spacing. So a transition from dendritic to cellular structures occur at cooling rates around 10 to the power 5 Kelvin per second in case of atomization based powder production. So this is the schematic which is showing comparing the cooling rate versus dendrite arm spacing in the powder particles. So you can see so the cooling rate is much higher in Gunsplat water atomization, it is higher than the gas atomizations, and subsequently we are achieving finer microstructure of the powder particles in the water atomized powders, which then otherwise impact the microstructure in the post sintering in the densified part. So that's why it is of course we can achieve improved sintering densification and improved mechanical properties in the powders developed via water atomization route compared to that we can get in case of gas atomized powders. So this is what is so then continuing with non-equilibrium structures. So high cooling rates can produce microcrystalline, amorphous and metastable phases. So these enhance sintering and are desirable for advanced applications. Rapid solidification methods, so techniques like droplet impact disintegration that we have discussed, this is one of the, as in the beginning of the atomization processes. Planar flow casting and melt extraction utilize chill block cooling, so achieving extremely high cooling rates. So these are widely used for materials like steels, copper, magnesium and aluminum alloys. So what is the importance of rapid solidification? So rapid solidification processes are gaining importance due to their ability to create very fine microstructures and improved material properties, making them suitable for various industrial appliances. So for the gas and liquid atomization techniques, cooling is enhanced by convection. So the cooling rate can be depicted as dT derivative of temperature, the time derivative of temperature is equal to 6 into H Ts minus Tg by rho g Cg dd. So this is the droplet diameter and here H is the convective cooling coefficient, and which closely depends on the relative velocity of the particles in the atomization fluid, and C and rho are respectively the heat capacity and density of the atomization gas. So rho g and Cg. So and Ts and Tg is of course the melt temperature and atomizing gas which is used the fluidized as a fluidization media. So then these are the typical comparison of the shape morphology of the typical powder particles which are produced by different atomization techniques. So you can see these are, I mean, A, B are the powder particles which are manufactured by gas atomization technique. So you can see irregular shaped powder particles that are generated in case of gas atomization. So if you recall, then so these are the particular powder types which can facilitate higher compression, I mean green compact strength, I mean and higher green density because of improved interlocking. However, their sintering performance will be poor than the, I mean rotational atomization and water atomized powders which are shown over here. So these are the, I mean spheroidal powder particles that we are as seeing observed over here. So this is a typical example of water atomization, and then sorry, this is a typical example of gas atomization, and this is a typical example of rotational atomization. So I mean that we have discussed earlier. That means it is a, I mean centrifugal powder atomization technique that we can achieve as, I mean completely spheroidal powder particles. So if you talk about the order of improvement, then we can talk about so I mean we are getting, I mean in gas atomization improved morphology than the, I mean water atomized powders. So you can see there is a combination of spheroidal powders and also there are some smaller particles. So that means there are more satellite powder particles observed over here. So that signifies as a bimodal distribution. So if you recall about the distribution earlier also, that particle size and frequency, so it is mostly like this, and that can cause variational green density if we use this kind of powders, and also in turn variational sinter density in post sintering, and also it can cause anisotropy in properties in the sintered parts. Whereas in case of the powders which are having, I mean uniform size distribution, having spheroidal powder particle shape and size, they can provide much higher, I mean sinter density and mechanical and physical properties. Okay. So with this we are done with the atomization aspects. So now we will discuss closely about the sintering mechanism. So sintering, it is basically may be considered as the process by which when assembly of particles compacted under pressure or simply confined in a container chemically bond themselves into a coherent body under the influence of an elevated temperature. So the temperature is usually below the melting point of the major constituent. So densification or shrinkage of the sintered part is very often associated with all types of sintering. However, sintering can take place without any shrinkage, but generally it deals with shrinkage. So, what are the steps involved? So, it is a complex process. So, the steps are initial bonding among powder particles, number 2 is neck growth, number 3 is pore channel closure, then pore rounding, then densification or pore shrinkage, and finally pore coarsening. So, these are basically the steps that we followed in case of sintering. So, then so solid state sintering deals with the bonding of powder particles forming necks, shrinkage of the compact due to decrease in porosity and change in pore geometry, and so this is the stages marked over here. Number 1 is initial point contact, number 2 is early stage neck growth, number 3 is the late stage neck growth, that is it happens after a long time when diffusion is allowed at the isothermal sintering temperature, and number 4 is the terminal condition, that means fully quali spheres, that means for a prolonged time when they are kept. So, then we can see fully quali sphere. So, in case of solid state sintering, bonding of powder particle is responsible for forming neck. So, please recall we have talked about the cold welding during the compaction stage between the neighboring powder particles. So, these are typical examples of cold welding from which serves as the locations or region where from the neck initiation happens during sintering densification. So, shrinkage of the compact due to decrease in porosity and change in pore geometry. So, then isolation of pores followed by homogenization of composition and grain growth with elimination of residual porosity. So, the driving force for mass transport is equal to change in surface energy by reduction of surface area. So, that is the driving force for mass transport happens in case of sintering densification. Okay. So, corresponding change in free energy of the system, that is dE is equal to gamma dAs. So, that is variation in surface curvature which occurs with the growth of the neck that joins individual powder particles. So, which causes variation in surface curvature, energy change with respect to change in volume dV at the neck. So, then if we differentiate with respect to the volume change at the neck, that is dE by dV, then we can write here as gamma dAs by dV. So, then we can write like this. So, then we can further simplify to this is equal to gamma 1 by R1 plus 1 by R2. Okay. So, so then this is basically so these are the driving forces for sintering. So, you can see this is the coalescence between two neighboring powder particles, the neck formation, that is so then change in chemical potential between two curved surfaces happen due to gradient in vapor pressure P and vacancy concentration C. So, which is shown over here. So, then so change in chemical potential, that is mu minus mu 0 is equal to RT ln P by P 0, which can also be expressed as mu minus mu 0 is equal to RT ln C by C 0. That means, it can be expressed in terms of the pressure, vapor pressure P, and also by the vacancy concentration C. Okay. So, the mass transport mechanisms in sintering. So, sintering of two spheres of the same diameter can be described as x by a to the power n is equal to k a to the power minus m into t, where a is the particle radius, x is the radius of the neck, and t is the sintering time. Okay, where small n, k and m are the rate controlling constants. So, the diffusional creep, which is also called as Nabarro, Herring and Koble creep, involving lattice and grain boundary diffusion, plays a major and dominant role. So, where Nabarro Herring creep, so stress directed atomic diffusion. So, in this case flow of vacancies atoms from GB tensile. So, one thing to be remember here. So, like we are talking about neck formation between neighboring powder particles. So, you can see there is a concave region and there is a convex region. So, the stress generated which is also can be called as sintering stress between the neighboring powder particles. So, in the concave region, it is mostly tensile in nature, that means positive, and in the convex region it is compressive in nature, so it is negative. So then so the flow of vacancies atoms from GB tensile, so that means from the concave region, concave boundary, so that the boundary, grain boundary forms at the concave boundary, it is the GB termed as GB tensile, and is the convex boundary, that is termed as GB compressive. So the Coble creep is due to grain boundary diffusion. So the mass transport mechanisms in sintering, so it is very beautifully marked over here. You can draw your attention over here. So it is happens, there are several mass transport mechanisms that are that generally happens in case of sintering. So number A is the lattice diffusion from grain boundary, B is the lattice diffusion from surface B, and then C is the lattice diffusion from defects. So this is a typical dislocation which is shown as a defect over here. Boundary diffusion from grain boundary, so where it is D, so this is from GB, boundary diffusion from grain boundary. E is the surface diffusion from surface, so you can, so this is basically E. And then vapor phase transport is the gaseous media, we have already discussed that we do sintering in the presence of a gaseous media, so which promotes vapor phase transport. So these are the different mass transport mechanisms that are that are generally responsible for sintering densification of the powder aggregate. So additional chemical driving force in a multi component system due to differences in diffusion rates. So that is, we can so additional chemical in a due to differences in diffusion rates are also possible. So which is caused by the inhomogeneous composition at the neck, at least at the first stage of sintering, porosities at sites where the faster diffusing species have migrated. So which is called as Kirkendall porosity. So these are like additional chemical driving forces in multi component systems that are also can be responsible for promoting sintering, but otherwise these are the mass transport mechanisms that are responsible for sintering densification of powder aggregates. So we will discuss about further details and the mechanism of different densification mechanisms in case of sintering densification in the next class. So we are stopping here for this class. So till then, and thank you.